Hello everyone. So this presentation is about proving the lower bound of element distinctness problem. This for course COT 5405 under Dr. Sharma Tankachan. So the element distinctness problem is about finding if all n elements in a given array are unique. That is distinct. So if all elements in the array are distinct, that is no two elements are the same, then we can say yes or else we can say no. So this is the decision problem. So we can use comparison as a model of computation. Comparison can be done in constant time for two elements. If either the element is less than or equal to the other element, or if element is greater than or equal to the other element, if they are equal, that means two elements are the same. We can simply say it is a no, or else we can simply say it is an S. So this can be solved by sorting the array. Sorting the best sorting algorithm takes order of n log n time. So this can be solved in order of n log n time, and we need to prove that the lower bound is order of n log n and no algorithm can do any better than n log n. We need at least n log n time to prove that all elements in the array are distinct. So the straightforward solution would be comparison of each element with the rest of the elements in the array. This would take at least n square time. We will reduce the number of comparisons by sorting the array so that if there are any same elements, they will come just next to each other. So we can simply compare the adjacent elements, like one first element with the second element with the third element. So we can compare the adjacent elements, and we can say yes if no two elements are the same. We will be like no if there are same elements. So to prove the lower bound, I'm going to prove the lower bound for the sorting, that at least sorting takes at least n log n time, and we need at least n minus 1 comparisons to show that all elements are distinct. So I'm going to do it in two steps. Together I'm going to say that at least I need n log n time for element distinctness problem. So any comparison based sorting algorithms, we just take the binary tree with nodes where we compare two elements. If it's an S, the decision tree will move on one side. If it's a no, it will go on the other side. So we just execute from root node to the leaf node, and in the end of the tree we get the leaf nodes, right? So that will be our answer. So leaf nodes hold the result for us. So we need to prove that this takes at least n log n time. So here I will explain the whole process using a small example of sorting three elements using a decision tree. I'll take first two elements, compare them with each other. If the computation is said to be an S, so I'll just compare the second element with the third element. If it is said to be an S again, so I'll give the sorted order like first element is smaller than the second element is smaller than the third element. So this is the first sorted order. So if it is a no here, then I have to compare the first element with the third element again. So depending on the yes or no of the computation, I just give two sorted orders again. So similarly, I just give the decision to be an yes or no of each node. Depending on that, I get different sorted orders. So different permutations. So I got like 6 permutations. Sorry. So I got 6 permutations for 3 nodes. So the height of the tree is the maximum number of nodes possible for this tree can be 2 power h, that is 8. So if there is a node here, then there will be like other 2 nodes coming out of this. So the maximum number of nodes possible will be 8. So the maximum number of possible is 8, but the max we got only 6. So this is the observations from this tree. So from the previous observations, I just wrote them down. Here we can simply say that 2 power h is greater than or equal to n factorial. That is, we got 8 as the maximum number of nodes in the previous problem for n is equal to 3, and we got 6 number of possible nodes. So number of leaves or 6. So the number of possible nodes are 8, but we got only 6. So we just derive at this generalization that 2 power h is greater or equal to n factorial. Here I'm solving for the value of h. I took logarithms on both sides, and then I just rewrote this for as a summation function. I took two summations from, I just divided summation into half, and then clearly this value is greater than this value, so I just wrote greater or equal to. this summation will run from n by 2 to n for log n by 2 value. So here from here I just wrote n by 2 log, so this will run for n by 2 times, so n by 2 log n by 2, h is equal to at least n log n. So to go from the root to leaf, we need to go through all the tree. For at least in the worst case, to reach the last possible leaf node, we need to go to the height of the tree, which is n log n. So at least we need n log n comparisons in the worst case for any comparison based sorting algorithm. Here in the second step, I'm just showing that we need at least n minus 1 comparisons after the sorting. After sorting, we need to compare the adjacent elements. So we need at least n minus 1 comparisons for this. To show that, I just before proposing the lower bound, I just gave the brute force approach for this entire list. So n minus 1 comparisons. So I'm trying to prove it can't get any better. So I just took n minus 2 comparisons, just assuming that we can do this in an n minus 2 comparisons using an algorithm A which exists. I'm assuming so. So I'm just taking an array X which have elements xi is equal to 2i for I is equal to 1 to n. So I'm assuming that all elements in this are unique. So first I'll run the algorithm A on input x. So it will take only n minus 2 comparisons because I'm taking xi is equal to 2i. So there is at least one element left out which is not compared to its next element. So first I'll find that element which is not compared to its next element, and then I will set xi is equal x of I plus 1 is equal to 2i. So x of I plus 1. Earlier it was x of I is equal to 2i. Now it is x of I plus 1. So x of I plus 1 is equal to 2i. Earlier when xi is equal to 2i, if I increment x of I plus 1, it will be like 2 of I plus 1. That is what I wrote here. So if I rerun the algorithm will give me the same output as it gave me when I run for this particular argument. It will give me the same output, which is not correct. So simply I can say that there cannot exist any correct comparison based algorithm which can find duplicates. That duplicates the same of repetition, right? So we need at least n minus 1 comparisons to say show that there are no duplicates in the sorted array. So there's a research paper given as a reference. So there they are defining two tree computation models. Out of them, one is algebraic computational tree T of n. So they're defining T of n. So it has two kinds of internal nodes. It's two kinds of internal nodes. So in that, first computational nodes, they're defining it as V, are of out degree 1. So they are labeling those nodes in the form of instruction. They're defining the instruction f of v tends to a some degree b. Okay, so they are defining this function as this belongs to plus minus. So they're just giving some basic computations. So it can be anything. So they are just labeling the v nodes as this function. So here they're defining a and b may be the real numbers, real constant, that is xi or fu, and u is an ancestor of v. Comparison nodes v, and then there is a second type of node. This is the first type of node they are defining with this instruction, and the second type of node, it has the out degree 3. So earlier it was only of out degree 1. So here the out degree is 3. It is labeled by xi or fu. Similarly, u ancestral of v, ancestor of v, and here the outgoing edges are plus, minus, and 0. So every node they are making some computations. If it's a plus, it's the tree goes on the one side, the addition goes on the other side of negative, and on the 0 it comes on the third edge. So this is what they define the algebraic computational tree T of n with two types of nodes. And now branching is occurring by comparison of nodes, whether if it is a positive or negative. So if it's a positive, it goes on the other side. So here, this is how branching is occurring. Here we are assuming that there is no zero division. We are eliminating this. It will be like a positive or a negative. So this is how they define the tree model T of n. Now they are just giving that for this model of tree, the height is again order of n log n. They're defining the height of n log n. So for this element distinctness problem, they are sorting either they are defining two methods for this particular tree T of n. So they are either sorting and comparing the adjacent elements just like before, or they are doing a different type of computation like pi I not equal to j xi minus xj. So this is what they are defining. This is how they are computing. So this is what here it's so this is what they are doing. Basically what they are trying to do is they are getting the difference of two elements from all the array and they are multiplying the differences. So this is the computation they are doing, algebraic computational tree. So they are getting the difference of two elements and then they are multiplying their products, multiplying the differences. Okay, so multiplying the differences. So it's like difference of two numbers here, difference of another two numbers here multiplied by, and so on. It keeps going. If any of the difference is zero, the whole product will be zero. That means there are at least one duplicate in the given array. That means the elements are not distinct. There's at least one similar element, one repetition. If the product is not equal to 0, that means the elements are distinct. We can simply say yes in this case. We can simply say no in this case. So for this tree, they are defining the RAM restrictions. They are proposing the RAM to be unrestricted, at least for arithmetic operations of addition, subtraction, multiplication. All these things can be cost and unit cost. So they are using the unrestricted RAM for indirect addressing, which makes this problem all important. So this unrestricted RAM specification is very important to solve this element distinctness problem. So this is what I understood from the research paper. I really like this approach from all other different types of computations they did. So I will wrap with this. I just gave my references, everything I followed here. Thank you.